Hi, it's my pleasure speaking at SNIA SDC Conference 2022. Myself, Kaustubh Katruwar, Senior Software Engineer with IBM Systems Lab. I work on container native storage technologies. Along with me, I have my colleague and co-presenter Sasikanth Ada, who is a cloud storage engineer and master inventor with IBM Systems Lab. Welcome to our session on architecting multi-cloud storage solutions. What are we going to cover today? We are going to talk about what has fueled the rise of multi-cloud adoption across organizations. Then we'll learn about the challenges faced by the organizations while steering through multi-cloud strategy. Amongst the fastest growing trend on multi-cloud is use of container technologies like Kubernetes, OpenShift and others. It has become an essential part of all the cloud strategy discussions. We will then look at the share of different workloads running on containers on Kubernetes. Then understand the best practices to follow in a multi-cloud Kubernetes deployment. We will be looking further into how storage is provisioned for the containers running in Kubernetes on a single cloud. Then we'll walk through our proposed architecture addressing the complex problem of managing storage for containers running in Kubernetes on a multi-cloud. We will read out a proposed Kubernetes storage operator design to help achieve this functionality. What is multi-cloud? It's the use of services from more than one cloud vendors. What is hybrid cloud? Hybrid cloud is the use of both public cloud and private cloud environments. Multi-clouds and hybrid clouds are not mutually exclusive. In fact, most hybrid cloud deployments are hybrid multi-cloud. Honestly, the conversations involving cloud today are actually about multi-cloud and hybrid cloud. The future isn't just cloud, it's multi-cloud. Gartner predicted a while back that by 2021, over 75% of mid-size and large organizations will have adopted a multi-cloud and or a hybrid IT strategy. Guess what? Fast forward today, it has all turned true. Rather, the numbers are a bit on the higher side than 75%. What has led to the rise of multi-cloud adoption? There has been an increase in demand for the computing services, compute, storage, all backed by increased digitization across spectrum of industries. We get flexibility with the choice to select best-in-breed services across clouds. Let's think about what are the prominent cloud vendors well known for. Think about AWS, EC2 instances comes to our mind. Talk about GCP, ML and DL services. Talk about IBM Cloud, Watson Studio, IBM Financial Cloud are the ones that come to our mind. There is an increase in resiliency or reliability of services when distributed across clouds. A better disaster recovery handling and business continuity is thus achieved. Reduced vulnerability to outages and unplanned downtime is what you get with multi-cloud deployments. With all workload in single cloud, there is a fear of being vendor locked. Moving out of such an arrangement is difficult and costly affair. Also, organizations can choose best services for them at a competitive price from different cloud vendors. So these are not just only few reasons why multi-cloud strategy has failed to growth. Multi-cloud has its own set of challenges. Broadly, those can be categorized under operational complexity, deep skills and expertise requirement, security and controls maintenance, budget. What are the factors that complicate multi-cloud strategy? Application onboarding across multiple clouds, encompassing one or more services, can quickly turn complex to handle. To effectively manage applications and resources across the clouds, unified, central, common console for management is most desired for. Managing updates to application translates to understanding and handling change management behavior of services across the clouds that they are hosted on, combining and visualizing events from monitoring, logging, and auditing tools to achieve a singular view and to prepare consistent response is difficult. Each cloud vendor and the service used will generate a separate bill and will have its own billing cycles. It can be easy to get lost and keep track of actual usage to confirm against the charged bills. Achieving operational excellence and adhering to SLAs is tough. Deep understanding of operational behavior for per cloud and expertise is needed. Organizations want to automate and define a policy driven workflow for their operations. Heterogeneous nature of multiple clouds vendors brings in a lot of complexity. With multiple clouds, there is more integration work for seamless but restricted access to services as desired. Each cloud vendor brings in its own technology implementations and security tools to handle application and user access. These are not the only limited challenges that mar the multi cloud strategy. Container technologies are no longer just the bleeding edge tech, but a clear platform choice for today and future. The container technology usage trends suggest that the top three workloads deployed on Kubernetes are databases or data caching solutions, artificial learning, artificial learning or machine learning software, and web servers. Each cloud provider has its preferred mechanisms, the command line interface, orchestration workflows that one must use to deploy their applications. These differences make deploying the same application to multiple cloud providers in an automated fashion difficult. The need for consistency across clouds favored most customers to adopt Kubernetes, the container technology platform. Kubernetes provide uniform and identical tools across cloud providers. Managing Kubernetes, however, in a multi-cloud environment can be challenging and requires the implementation of best practices. There have been many challenges using Kubernetes across multi-cloud or hybrid cloud environments. Some of them have been around, like how do you appropriately label your workloads, how do you appropriately label your nodes, how do you control isolation or distribution of workloads, right? Then the service exposures, like what kind of services you want to expose, say to public interfaces or private links, and what's the network between the multi-cloud, how do you auto scale your workloads and applications across multi-clouds, how do you have a uniform storage across these multi-cloud. In this discussion we are going to focus mainly on the storage aspect, storage for containers on Kubernetes. So if you see the storage management within a container Kubernetes cluster in a multi-cloud environment means you have to rely on CSI, container storage interface. So one container storage interface per cloud deployment. With more clouds, adoption of more cloud environments, more CSI environments to manage, that itself gets overwhelming. Now let's have a look at how a typical single cloud Kubernetes setup will look like. We will have cloud VMs acting as the worker nodes. These VMs can be bare metal servers or VMware machines. Let's consider VMs in our discussions. These can be shared or dedicated VMs. Then there shall be Red Hat or Arcos or a flavor of Linux operating system on top of which Kubernetes or OpenShift cluster is deployed. This forms the compute element. Storage is coming from a different service. SAN or volume controller is responsible to virtualize the physical drives to expose the volume LUNs. The container storage interface or CSI component in the Kubernetes cluster doing the storage management, which has sidecar containers like registrar, provisioner, attacher, resizer, snapshotter is doing the block volumes. Now looking at the top workloads on containers on Kubernetes, databases show up on that list at the top. Database needs performance. It comes from raw block volumes. Hence, it drives the need to have a raw block volumes. Now consider all the application pods are database pods. They shall have a volume claim and are having a volume mount which is serving the raw block volumes. The problem with raw block volume is, say we want to modify the storage, add or reduce the storage capacity. The application, which is containerized application, has to hence recycle. The storage is not a first class citizen. Memory and compute are the first class citizens in the environment. The control virtualization needs to recycle the application pods so that the volume claims can be added or removed. Kubernetes is a dynamic environment, whereas the storage is not designed to behave dynamically to changes. Talking about storage, the focus has been at how much throughput does the storage provides or how much time a triggered snapshot takes to complete. But we do not look at or measure how much time does the control path takes, how many parallel snapshot requests does the storage system can handle, how many PVC requests, how many raw block volume provisions is the storage capable to make up. These are all dynamic behaviors. Storage control path has never been designed for that. It has always been the IO path that has been the part to be optimized. Scalability limits from underlying storage. Within single cloud, the scalability is shunned by the limits of the cloud provider. For example, in AWS, the disk size limit is 16 terabytes with EC2, whereas in VMware, one gets a 64 terabyte disk size. So there are going to be scalability limits and one needs to adhere within that single cloud environment. Compute and storage infrastructure are two different services in typical clouds, because if you see, this all becomes Kubernetes services like EKS or ROSA or a customer managed service, and storage is coming from elastic block storage like EBS. So there are two different services to maintain here. Pods are not aware of storage changes. We just touched upon this point a while ago. Offloading computation to storage is not easy because everything needed has to come from the CSI driver only. The raw block volumes cannot be made intelligent. The only configuration entity or the interfacing agent here is the CSI driver. Administration of difficulty to manage on-premise storage hardware. Assume we have a private cloud environment. Then we have to set up and manage the storage provisioning system, which itself is again a painful activity. Security challenges, as we all know about. Then lacks enterprise storage feature controls and management. Every enterprise environment wants to have a complete control of the infrastructure which themselves. That's the reason why we see more and more managed services are coming up in cloud rather than the provider managed services or provided services. If we see from management point of view, enterprises want the entire control of their hardware. They want to configure features that they want or they like. They don't want things or discard those which they don't like or don't need. So this is something which is lacking when we go with a single cloud under traditional setup for Kubernetes. Here is our proposal on storage management for containers on Kubernetes in a multi-cloud environment. Storage integrated container in orchestration. So we are going to have some pods or workers which are dedicated and call them as storage pods. Looking at the previous diagram, we introduced the box in the center at the top, which would represent storage pods. These are the ones which shall be performing the raw block volume attachments. From here on, we have our own CSI, which is a file system CSI, exposing host paths to the other applications, the containerized applications hosted on the Kubernetes platform. So that way, Kubernetes cluster is more of a storage integrated. Let's check out how are we going to implement this kind of strategy. This kind of implementations are feasible and possible in Kubernetes world with the help of operator framework. Textual definition of operator It means provides a consistent interface, behavior access control, and semantics to define and implement lifecycle management across resource types and locations. Simply putting it, the goal of an operator is to put operational knowledge into software. It simplifies the use of management operations and maintenance, and hence leads to evolution of higher level automation and orchestration. The operator can be extended to implement and automate common day 1 activities like installation, configuration, and day 2 activities, the advanced features like reconfiguration, updates, backup, failover, restore for a multi-cloud environment. Quickly glancing through this image, a user would push a custom resource on the platform, which would be continuously observed by the operator. The operator would recognize this custom resource and spawn the necessary application pods. Any updates or changes to this custom resource would be recognized as the operator is tracking the custom resource, and then it tries to adjust the current state of the deployed application pods to match what has been submitted in the custom resource. In case of error, the operator would reconcile and try to adjust the state of the deployed pods to match the custom resource definition. Now let's have a look at how does this multi-cloud storage operator would look like and behave. We have a storage management operator which will designate few pods as storage or dedicated worker nodes, auto detect the underlying cloud platform and initialize the appropriate cloud storage interface. Then raw block volumes are provisioned and attached to these storage nodes. So this is one of the flows that the operator would design and would be responsible for another flow as well, where the same operator is responsible to configure a clustered file system, which can be any open source one like Gluster file system, Ceph, or others. And it can be also a proprietary one like the IBM's very own clustered file system, Spectrum Scale, which is a high performance, scalable, and enterprise ready clustered file system, which also suits to provide storage for the containers on Kubernetes platform. The file system is configured using the raw volumes that are created, which are provisioned in this step. And then we have this cluster file systems CSI, which is acting as a file driver CSI, exposing the storage over host paths. The containerized applications use this file system CSI to provision volumes to frame their pods or use their pods, right? So underneath this CSI is the interface to the provisioning of storage. The applications aren't aware of any storage aspects, and they need not be. They are only talking to the file server, or let's say the file system, where the operator is the one who is managing all the storage aspects internally within the environment. Thus, controller manages the file system install and configuration. It's responsible for replication of data across volumes, disaster recovery configurations, or any other rich file system feature configurations. Thus, it provides you an unlimited scalability as well. We'll go through some question and answers, if any, on the line. And thank you for being a patient crowd and actively participating on this session. Please take a moment to rate this session and provide your important feedback to us.